Two components to the challenge, one of them being the blind prediction of host-guest binding free energies. And this is the part of the contest that we participated in. And we calculated the binding free energies via the AMOEBA force field, which is a polarizable model. So a few take-home points that hopefully I'll drive home over the next 15 minutes or so. Why any of this following work for calculating the free energies is important. So overall, we're not examining a congeneric series. So we have a very diverse test set as part of the sample contest. And within the guest set, there are real drug molecules. So there's a huge variety of molecules that we're looking at. Also that within the system of interest, there's different environments, so we can really show off the polarizable model. Within our host, we have a hydrophobic interior and a polar exterior, and then also calculating the solvation energies of gas within water. And then finally, that the free energies that we're calculating are absolute free energies as opposed to relative free energies. So that we've heard some of the shortcomings of relative free energies. So to make a quick analogy, that we're not going to be calculating the free energies of taking an elephant and changing it into a rhino, that what we like to do is actually disappear the elephant. So slightly more difficult and hopefully more accurate as well at the end of the day. So for the sample 6 challenge, for the host-guest systems that were presented to us for the blind prediction, that the host system was a Q-cubital ring, so it had 8 units that repeated around the ring system. And then the guests, there were 14 different guests that were varying in size and charge and complexity. So that the guests here are what are considered the drug molecules then, and then a series of molecules down here that have some similarity to them. So the molecules that are highlighted in red were considered the challenge problems. And so for guests 11 and 12, that there was the possibility that more than one guest actually might bind to the host. So that was part of the challenge, was can you predict the correct ratio of guests binding to host? And then the guest 13, the oxaliplatin, had a platinum in there. So transition metal was supposed to be more difficult as far as calculating the free energies were concerned. Right, so in order to calculate our binding free energies, that we utilize the AMOEBA force field, so a polarizable model. And then we first need to generate the parameters for our the guests. And so in order to do that, we followed a typical AMOEBA protocol. And to do that, we did an initial quantum calculation at what we would consider a low level of theory, so MP2 with a Pobel type basis set, to get our initial guesses for the multiples, so our charges, our dipoles, and our quadrupoles. And then we ran a higher level ab initio calculation with MP2, but with a correlation consistent basis set. And then we fit our initial guess dipoles and quadrupoles to that higher level quantum, the electrostatic potential generated from that. And then to round out everything, we then had our valence parameters via fitting to the quantum calculations from the Merck force field, and then also from existing AMOEBA parameters. So once we had our parameters in hand for our guest system, we can then actually move forward and calculate our free energies. And in order to do that, we utilized the dynamic program and the bar program via Tinker OpenMM. And all of these were run on GPUs. And so that I really can't drive home enough how life-changing the utilization of GPUs are within our free energy calculations, because just a few years ago that we were running everything on CPUs, and I can't even imagine now trying to do that. So it's great, the enhanced sampling that we can get just by running longer simulations on the GPUs. So just to put a number to it, that these calculations run about 20 times faster on the GPUs that we have in-house now. So. Okay, so within our simulations, our host guest systems were placed within a 40 angstrom explicit water box. We're utilizing the RESPA integrator, and our simulations were run for 10 nanoseconds. We did bar to calculate the free energies, and we tossed out the first nanosecond as equilibration, and then looked at monitoring the forward and backward FEP for any type of hysteresis. And this would be the indication if we needed to run any additional windows as we're turning off the electrostatics and the van der Waals. So with respect to turning off the electrostatics and the van der Waals, that we would first annihilate the electrostatics and then decouple the van der Waals. And I'll comment more about this protocol in a little bit. So then we also, for the host-guest system, that we implemented a flat bottom harmonic restraint between the host and the guest. And the distance for this restraint was defined after running a long unrestrained simulation between for the host-guest system. And then at the end of the day, doing all this to calculate our absolute binding for energies then. Okay, so we made our submission to this, this blind challenge, and then these were our initial results. So we see some encouraging results here, but then we see some huge outliers, and these actually happen to be some of the drug molecules that were in the test set. One thing that we did do well on was predicting the correct ratio between the guest 11 and guest 12 with the host. So we predicted a 1-to-1 ratio for guest 11, and then for guest 12, we accurately predicted that there would be 2 guests that would bind to the host. But at the end of the day, we'd like to see better results than this. So we were wondering what was wrong with our predictions. So were there problems with the parameters, or were there problems with our actual protocol that we had implemented? So we then went back and looked at our results further, looked at analyzing some of the simulations, and we noticed that for one of our huge outliers, guest 2, then when we were at the 0-0 level, so where we had annihilated the electrostatics and decoupled the van der Waals, that we actually had 2 different conformations for our guest system. So our guest, when it was by itself solvated, took on this conformation. The guest within the host guest system at the 0-0 level had a different conformation. So we actually weren't comparing apples to apples at the 0-0 level. That we needed to figure out a way that we could rectify the situation and see better sampling of the 2 conformations at the fully decoupled and annihilated level. So in order to do that, we tested a few different things that we could do to change our protocol. So the blue curves here are where we just decoupled the van der Waals, so we still had some intramolecular van der Waals present. And this is where we have our 2 distinct conformations at the 0-0 level. If we then annihilate the van der Waals as well, we'll see the green line here. So we're starting to see better sampling of the 2 conformations at the 0-0 level. And what would be considered a final solution for this would be if we also then zeroed out a key torsion within the molecule. And so then we get that free rotation around that torsion. So we'll see then sampling, this red line here, sampling both conformations in the guest solvated and then also the guest and host guest system then. So then to resolve the problem where we saw the guest locked in 2 different conformations, that we decided to continue with annihilating the electrostatics, also annihilating the van der Waals. And then if there is this key torsion within one of the molecules, for example, this key torsion here in guest 2, that we would then scale this down to zero it out during the annihilation of the van der Waals. Okay, so we looked at tackling one of the problems potentially with our protocol. So were there any problems with our parameterization? And so what we observed for the Q-cubital ring is that we were actually observing indentations, either a single or a double indentation of the ring over the course of time. And this is something that we decided was potentially non-physical because this wasn't observed in any crystal structures of the CB8 or the CB7. So we decided that we needed to figure out a way that we could better represent the fluctuation of this ring. So in order to do that, we looked at zeroing in on some of the torsion parameters of the Q-cubital. So there's 8 repeating units around the ring. So this key torsion here is one that plays a significant role in describing the fluctuation of the ring. So what we did was we went back and then calculated the energetics via DFT of various conformations of this Q-cubital ring. So the CB7, the CB8 with a single or double indentation, and looked at the energetic differences and then varied our torsion value based on those differences. So our initial submission had the threefold torsion value at negative 0.25. And so there's obviously, compared to the quantum, there's some huge differences here. So when we look at increasing that torsional value there to negative 1.5, 1.6, 1.7, you see there's better agreement with quantum. So at the end of the day, that we decided to increase that torsional value to negative 1.6 to get better agreement with quantum that would hopefully have a better description of our Q-cubital ring system. This is also reinforced when looking at the ring and then pulling it into an ellipse shape. So again, trying to just make sure we're getting this fluctuation of the ring described properly. So we had 2 different elliptical shapes here. again, running quantum calculations to get those energetics, and then observing that our proposed new torsional value of negative 1.6 is in better agreement with quantum than what our previous torsional value was for the q-cubital 8. Okay, so at the end of the day then, what we learned from the sample contest was that we needed to look at reanalyzing our torsional values and then also figuring out if there were any problems within our protocol. And so what we did then was modified the CB8 torsional parameter to get a better description of the fluctuation of the ring, and then also switched to a double annihilation scheme and then potentially zeroing out any key torsions if we had a floppy molecule. And so examining the raw numbers then, that we went from having an absolute deviation of 2.7 to, with these modifications to our methodology, having a deviation of 1.23. And then also that for some of our huge outliers, guess 2 and guess 3, that they benefited from this greater sampling of the guess conformation, as well as from modifying the fluctuation of the CB8 to get a more accurate description, and that our 2 outliers then are in better agreement with the experiment. All right, so just to look at it graphically then, we see that our outliers are now in better agreement with the experiment. And these weren't just changes, again, that we made to the methodology because that these were just outliers and this is going to just fix this problem. That these are changes to the methodology that we can put into practice for future calculations then, and then hopefully be able to get this type of accuracy right off the bat when we do any kind of blind prediction. So also that 8 of our 15 predicted energies were within 0.65 kcals per mole. Okay, so now that we have confidence in our model, we think we have a good energetic model as far as parameterization is concerned, and also our binding for energy protocol, that we want to look at moving forward to larger systems. So looking at the FXR that was part of the actually with the sample 4 contest, where there was prediction of the binding poses as well as prediction of the binding for energy. So there are over 100 IC50s that are available with crystal structures. So looking at applying our methodology to those systems. Also then considering calculating relative for energies with our model. For the FXR, that all the other predictions were with relative for energies, so to make a good comparison with them. And then also down the line, if that's something that's more applicable to our system of interest, we can look at calculating relative for energies. And finally then, looking at entertaining different sampling options, so whether it's going to be some enhanced sampling methods like OSRW, implementing TCG within our methodology, potentially looking at hydrogen redistribution, different ways that we can cut down on the time of our calculation. Okay, so in the last seconds that I have then, so what I started with, that hopefully I've demonstrated that we have an accurate methodology. So when we're looking at a non-congeneric series here, so being able to accurately predict interactions that involve drug molecules, we are able to make accurate predictions when we have different environments within our host and our guest system, and then that we're also able to accurately calculate our absolute binding for energies as opposed to just relative for energies. So with that, I think my PI, Jay Ponder, and then also if you want to talk any more about the sample contests, we participated in 6 and also have results from sample 5 for predicting binding for energies, and we'll have a poster later. So, and thank you for your time.
Any questions?
Yes.
Could you just comment about the size of your error bars associated with repeatability of the calculations?
So we're seeing about a quarter of a kcal as far as errors associated with our calculations. So when we've gone back and rerun everything with our new standard protocol. Yes. Yeah.
Mike Wilson has been doing some cool work using the actual host-guest ITC measurements or thermodynamic measurements to actually improve force field parameters. Have you folks thought about trying to go back and fix some of the issues with including that information in force field parameterization updates?
Right. We haven't yet, but that's definitely something that's definitely doable. So, yeah.
Any other questions? Okay, let's thank Marie again.